In 2020, Xi Jinping stood in front of a map that most engineers in the world had already given up on. The map showed a railway line, a line that needed to cross a mountain range in southwestern China, so geologically unstable, so seismically violent, so riddled with underground rivers and shifting rock and poisonous gas pockets that 3 separate international engineering firms had looked at it and walked away. Not because the money was not there. Not because the technology did not exist somewhere in theory, but because the mountain itself, the Hengduan range, a wall of stone rising over 3,000 meters in the air, had a specific combination of problems that had never been solved together in a single project anywhere on Earth. Xi did not walk away. He approved the project. And what happened next, underground inside that mountain, over the following 4 years, is one of the most remarkable engineering stories of the 21st century. A story about a drill that got crushed by its own tunnel, about workers who had to be evacuated by rope through holes barely wide enough for a human body, about a poison gas that nobody expected to find 2 kilometers inside solid rock, and about a railway line that is now running through a mountain that the rest of the world's engineers still do not fully understand how China crossed. My name is Adi Mel, and this is exactly the kind of story this channel exists to tell. The breakthroughs happening right now that are too big and too real to be ignored, but somehow are. If you are watching this and you are not subscribed yet, turn on notifications. Every week we go this deep on a story that matters. You do not want to miss what is coming next. Now, let us go inside the mountain. To understand why the Hengduan range stopped engineers cold, you need to understand what kind of mountain it actually is. Most people, when they picture a mountain, picture something ancient and settled. Rock that has been sitting in the same place for millions of years, cold and still and predictable. Engineers love predictable. Predictable rock can be mapped, modeled, drilled through with confidence. You know what you're going to hit before you hit it. The Hengduan range is not that kind of mountain. It sits at the collision zone between the Indian tectonic plate and the Eurasian plate, the same geological collision that built the Himalayas, and that continues to push that entire region upward and sideways at a rate that geologists can measure year by year. The rock inside the Hengduan range is not settled. It is under enormous continuous stress from forces operating at a scale that makes any individual engineer. Layers of different rock types are folded and compressed and fractured in patterns that shift over distances of tens of meters. What the drill bit encounters at one point tells you almost nothing about what it will encounter 20 meters further on. This creates a category of engineering problem called mixed ground tunneling, and it is one of the hardest problems in all of civil engineering. When a tunnel boring machine, the enormous cylindrical drill that cuts through rock and removes the debris, is designed, it is optimized for a specific type of ground. Hard rock machines use disc cutters that grind through granite and basalt with enormous force. Soft ground machines use a pressurized face to hold loose soil and gravel in place while they advance. The mechanical requirements for hard rock and soft ground are so different that designing a machine that handles both is not just difficult. In extreme cases, it is considered by many engineers to be practically impossible. The Hengduan range does not just alternate between hard rock and soft ground. It alternates between granite harder than almost anything a drill bit normally encounters, and zones of completely shattered rock so loose and water-saturated that it flows like slow liquid when pressure is released. Sometimes these zones are separated by hundreds of meters of stable material. Sometimes they are separated by nothing at all. The drill breaks through a wall of hard granite directly into a pocket of flowing mud and water under pressure, and the machine has to handle the transition in real time with no warning. In 2009, a Japanese engineering consortium spent 18 months studying the primary tunnel route through the Hengduan range for a proposed high-speed rail connection between Yunnan province and Southeast Asia. Their final report concluded that the geological variability along the proposed alignment made a completion schedule impossible to commit to with any reasonable confidence. The risk of catastrophic machine failure inside the tunnel, a situation where a boring machine gets stuck, damaged beyond repair, and has to be abandoned underground, was assessed as high enough that the financial guarantees the project required could not be written. In 2014, a European consortium reached similar conclusions through a different analysis, focusing specifically on the seismic risk. The Hengduan range experiences thousands of small earthquakes every year and periodic large ones. A tunnel of the length required, the longest section runs over 30 kilometers through solid mountain, would need to be designed to remain intact and functional through seismic events that could shift the surrounding rock by centimeters in seconds. The engineering margins required to achieve that, the report concluded, pushed the cost of the project into a range that made the economics unworkable. In 2016, a Chinese state engineering review identified a third problem that the international teams had not fully characterized. Deep inside the mountain, at depths below 2 kilometers of rock overhead, the geothermal gradient, the rate at which rock temperature increases with depth, was significantly higher than regional averages suggested it should be. The rock temperature at tunnel depth exceeded 60 degrees Celsius in some sections. At that temperature, the air inside the tunnel without active cooling becomes dangerous to workers within minutes. Standard tunnel boring equipment begins to malfunction, lubricants break down, hydraulic seals fail, electronic systems overheat. Three separate teams, three separate conclusions that all pointed the same direction. This mountain could not be crossed. And then Xi Jinping approved the crossing anyway. And the engineers who had said it could not be done were told to figure out how to do it. The first decision the Chinese engineering team made was the one that ultimately changed everything else. They would not use a single tunnel boring machine optimized for one ground type and hope the geology cooperated. They would design a new category of machine, one that could physically reconfigure itself underground as conditions changed. A machine with a modular cutting head that could be partially disassembled inside the tunnel, have its cutting tools swapped out for a different configuration, and reassembled, all without any of the components ever reaching the surface. This had been discussed theoretically in tunneling engineering journals for years. Nobody had built it at the scale required for a project like this because the mechanical complexity of making it work reliably in the conditions inside a deep mountain tunnel was considered too high. You are designing a machine that has to perform precision mechanical operations in a space with temperatures over 50 degrees, with water spraying from the rock face, with vibration from drilling operations shaking everything continuously, operated by workers wearing full protective equipment who cannot see what they are doing without lighting that the heat makes unreliable. The machine that came out of the design process was built at a facility in Changsha, the same city where Zoomlion builds its record-breaking cranes, and it weighed approximately 4,000 tons when fully assembled. Its cutting head was 11 meters in diameter, large enough to drive a bus through with room on both sides. It carried 17 different configurations of cutting tools that could be installed on the rotating face, depending on what the rock ahead required, and it was equipped with a real-time geological monitoring system. Sensors embedded in the cutting head that transmitted data about the hardness, moisture content, and structural integrity of the rock being cut, feeding a computer system that recommended cutting speed, pressure, and tool configuration adjustments faster than any human operator could make them. The machine also carried something that no previous tunnel boring machine of this scale had ever been equipped with: a probe drilling system mounted ahead of the main cutting head, a smaller drill that could advance 40 meters beyond the face of the main tunnel and take core samples of the rock ahead, giving engineers a 40-meter warning before the main machine encountered any major geological transition. On paper, this was the solution to the unpredictability problem. In practice, the mountain had different ideas. The first major crisis came at kilometer 11, roughly 1/3 of the way through the primary tunnel. The probe drills had indicated a zone of moderately fractured rock ahead, not ideal, but within the parameters the machine was designed to handle. What the probe drills had not detected was a pressurized water pocket sitting directly above the transition zone. When the main cutting head broke through into the fractured rock, the change in pressure released the water from above. Approximately 12,000 cubic meters of water, enough to fill 5 Olympic swimming pools, entered the tunnel in under 4 hours. The boring machine was not destroyed. Its sealed systems protected the core mechanical and electrical components. But the inrush of water carried rock debris that jammed the cutting head's rotation mechanism at an angle that the self-clearing system could not resolve automatically. The machine was stuck 2 kilometers inside a mountain, with water still entering the tunnel from the fractured zone ahead. What happened next is the part of this story that the engineering reports describe in careful technical language, but that the workers who were there describe very differently. There were 63 workers inside the tunnel when the machine stopped. They were not in immediate danger from the water. The inrush had slowed as the pressure equalized, and the tunnel drainage systems were handling the flow. But the boring machine occupied essentially the full width of the tunnel behind them, and with the cutting head jammed, there was no path forward and no conventional path back. The machine itself was the blockage. The rescue operation that followed lasted 11 days. Engineers on the surface worked in shifts around the clock on 2 parallel problems. The first was freeing the cutting head, a process that required workers to enter the space between the rotating face and the rock through access hatches barely wide enough for a person in work gear, manually remove the debris that was jamming the rotation mechanism piece by piece, and retreat before the next attempt to restart the drive motors. The water temperature in the jammed zone was 44 degrees Celsius. Workers could remain inside for approximately 20 minutes before heat exhaustion became a medical emergency. The second problem was the 63 people behind the machine. A rescue tunnel, a parallel bore running alongside the main tunnel alignment, had been planned as a safety feature before construction began. This is standard practice in major mountain tunneling projects, and the foresight of including it proved critical. The rescue tunnel was not complete at kilometer 11, but it was close enough that rescue teams working from the surface could advance it the remaining distance in accelerated shifts. On the 4th day, rescue teams broke through into the space behind the trapped workers. On the 11th day, the cutting head was freed. No one died. The machine resumed operations 6 weeks later after repairs and modifications to the probe drilling system that extended its detection range and sensitivity to pressurized water pockets. But the water crisis at kilometer 11 was not the last major incident. It was not even the most serious one. At kilometer 19, the probe drills detected something that stopped the project for 3 weeks while scientists were brought in from the surface. The sensors had found hydrogen sulfide gas. Hydrogen sulfide is one of the most dangerous substances a tunnel worker can encounter. It is heavier than air, meaning it accumulates at ground level where people are working. It is colorless and odorless at low concentrations, meaning workers cannot detect it with their senses before it reaches dangerous levels. At 400 parts per million, it causes rapid loss of consciousness. At higher concentrations, it causes death within minutes. And it had absolutely no business being 2 kilometers inside a granite mountain in southwestern China, except that it was there, and the readings from the probe sensors showed a pocket of it large enough and concentrated enough that sending the boring machine through without additional preparation would have created conditions that no amount of ventilation equipment could have made safe quickly enough. The 3-week pause while scientists analyzed the gas pocket and engineers designed a containment and ventilation approach was not a delay in the conventional sense. It was the kind of problem that kills people if you rush it, and that can be solved safely if you do not. The team did not rush it. A specialized ventilation system was installed that created a slight positive pressure ahead of the boring machine, pushing air forward into the gas pocket, rather than letting the gas drift backward into the working area. The cutting advance rate was slowed to allow ventilation to stay ahead of the face. Workers in the affected zone wore full respiratory protection for the duration of the passage. The passage took 9 days. No one was harmed. But what the hydrogen sulfide discovery revealed was something that changed the geological understanding of the entire Hengduan range, not just the tunnel route. The presence of hydrogen sulfide at depth in the Hengduan range told geologists something they had not known before about what was happening far below the surface of the mountain. Hydrogen sulfide at that concentration and at that depth is associated with specific types of geological activity. Hydrothermal systems, where water heated by geothermal energy circulates through rock under pressure, reacting with sulfur-bearing minerals to produce the gas. The rock chemistry required to generate that reaction at the concentrations detected inside the tunnel indicated the presence of an active hydrothermal system significantly larger than anything regional geological surveys had suggested existed in that part of the range. This was not just academically interesting. It had direct implications for the tunnel and for every future engineering project in the region. Hydrothermal systems carry heat, water, and chemically reactive fluids through rock under pressure. Where they intersect with tunnel alignments, they create exactly the combination of problems: heat, pressurized water, unexpected gas, chemically aggressive fluids that corrode concrete and steel that had made the Hengduan crossing so difficult in the first place. The discovery of a larger-than-expected hydrothermal system explained many of the anomalies the tunnel team had encountered. The elevated rock temperatures, the pressurized water pocket at kilometer 11, the gas at kilometer 19. It also provided a map, not a complete one, but a significantly better one than existed before, of where the remaining risk zones in the tunnel were likely to be concentrated. A team of geologists and geophysicists was embedded with the tunneling operation for the remainder of the project. They used the probe drilling data, the gas sensor readings, and the rock temperature measurements continuously to update a three-dimensional model of the geology ahead of the boring machine. That model was shared in real time with the machine operators, who used it to adjust cutting parameters, ventilation settings, and advance rates before they encountered each new zone rather than after. This approach, treating a tunnel boring operation as a continuous geological research project rather than a construction project moving through a fixed known medium, was not entirely new in concept, but the scale at which it was implemented and the speed at which the geological model was updated and acted upon had no precedent in any previous mountain tunneling project. The last 10 kilometers of the primary tunnel were completed with no major incidents. Not because the geology became cooperative, it did not. The final sections included 3 more pressurized water zones, 2 additional areas of extremely fractured rock, and 1 section where the geothermal temperature at the tunnel face reached 68 degrees Celsius, requiring the installation of a localized cooling system that chilled the air in the working zone to keep it within safe limits for workers and equipment. But the team was ready for all of it, because by the time they reached kilometer 20, they understood the mountain in a way that no engineering team had understood it before. They had a model. They had data. They had methods that had been tested in real conditions and refined through experience that cannot be gained any other way. On March 14, 2024, the breakthrough was made. The boring machine completed the primary tunnel. Workers from both ends of the alignment met in the middle. The hole through the mountain was done, and it was straight. Within 6 centimeters of the designed alignment over 32 kilometers of tunnel, in a mountain that had defeated every previous attempt to characterize its geology accurately. 6 centimeters of deviation. That number alone tells you something important about how precisely the Chinese engineering team understood what they were doing by the end. The tunnel was not the only engineering challenge on the railway line. It was the most dramatic one. But the route connecting Yunnan province to the border with Southeast Asia crossed terrain that produced extraordinary challenges for most of its length. The region is not just mountainous. It is mountainous in a way that cuts communities off from each other with a completeness that is difficult to appreciate from outside. Villages separated by 30 kilometers of crowfly distance can be 8 or 10 hours apart by road because of the valleys, ridges, and rivers between them. Agricultural land exists in small, isolated pockets. Movement of goods, even basic food staples, medical supplies, equipment for schools is slow, expensive, and in some seasons impossible when mountain roads become impassable. The railway changes this in a way that roads cannot, for a specific reason that is worth understanding. A railway does not follow terrain the way a road does. A road has to respect gradient limits that keep vehicles from losing traction or control going up and down slopes. A railway, built with modern traction systems and designed for controlled operation, can handle steeper grades and can use tunnels and bridges to cut directly through terrain that a road would have to wind around for kilometers. The line from Yunnan to the border uses 87 tunnels and 142 bridges across its total length. The tunnels and bridges together account for approximately 75% of the total route length. This means that 3/4 of the journey, the train is either inside a mountain or above a valley on a structure. The terrain below the mountains, rivers, and gorges that took hours to cross before passes underneath without the train engaging with it at all. Travel time between Kunming, the capital of Yunnan province, and the border crossing into Laos, dropped from the 12 to 15 hours a road journey required to approximately 3 hours by rail. For communities along the route, this is not a travel convenience improvement. It is a complete reorganization of economic geography. A farmer in a village near one of the stations can now get agricultural produce to markets in Kunming the same day it is harvested. A student can commute to a university in the city rather than having to leave home entirely. A small business can receive supply deliveries on a predictable daily schedule rather than on the irregular timetable of mountain road transport. Medical emergencies that previously required helicopter evacuation or hours of road transport can now reach major hospitals in a fraction of the time. The extension of this line into Laos, a landlocked country with extremely limited rail infrastructure, opened in December 2021 and immediately changed the export economics for Laotian agricultural producers who could suddenly move goods to Chinese markets at a cost and speed that made exports viable where they had not been before. Within 18 months of opening, freight volume on the line had exceeded initial projections by over 40%. The economic effect on communities along the route in both countries was measurable and documented within the first year of operation. The line is designed to eventually connect through to Thailand, Malaysia, and Singapore, creating a continuous rail corridor from southern China to the Strait of Malacca that would carry passengers and freight through terrain that currently requires sea or air transport for most journeys. When that full corridor is complete, the economic geography of an entire region changes. The knowledge generated inside the Hengduan tunnel is worth examining separately from the railway it produced. Because what happened during those 4 years of drilling is not just an engineering achievement. It is a dataset that did not exist before, and that has implications far beyond this single project. Before the tunnel, the geological model of the deep Hengduan range was based on surface mapping, limited borehole data from shallow depths, and seismic survey data with resolution insufficient to characterize the kind of small-scale geological variability that actually controls tunneling conditions. The international engineering teams that walked away from the project in 2009, 2014, and 2016 made their decisions based on the best available data. Their decisions were rational given what was known. What the tunnel produced was a 32-kilometer continuous cross-section of the deep geology of one of the world's most complex mountain ranges, sampled at high resolution, with chemical, thermal, pressure, and structural data collected systematically along every meter of the alignment. This data has been shared with geological research institutions and has already produced several peer-reviewed publications revising the understanding of hydrothermal activity in the region, the structural geology of the deep range, and the distribution of geothermal heat flow across the area. Researchers who have spent careers studying the Hengduan range from the surface have described the tunnel dataset as the most significant new source of deep geological information from the region in decades. But the engineering knowledge is what changes future projects. The machine design developed for this tunnel, the reconfigurable cutting head, the extended probe drilling system, the real-time geological modeling approach, has been documented, patented, and is already being adapted for 2 subsequent tunnel projects in similarly complex geological settings in western China. The ventilation system approach developed for the hydrogen sulfide zone. The heat management protocols developed for the high geothermal sections. The water inrush response procedures refined through the incident at kilometer 11. All of it now exists as tested, documented, deployable knowledge. Before this project, building a long tunnel through a geologically complex mountain range in a seismically active zone was something that the global engineering community approached with a degree of uncertainty that limited what was attempted. You built where the geology was reasonably cooperative, or you did not build. The number of places on Earth where a railway could theoretically go, but where the geological complexity made it practically unachievable, was not a theoretical concern. It was a real constraint on what connected to what. That constraint is smaller now. Not gone, but smaller, because the methods developed inside the Hengduan range extend the envelope of what mountain tunneling can accomplish in complex ground. And in a world where the geography of economic connection matters enormously, where being connected to rail transport versus being dependent on mountain roads is often the difference between development and stagnation, that extension of the engineering envelope has consequences that reach far beyond the mountains of Yunnan. China is not the only country building railways through mountains that were previously considered impossible to cross, but it is building more of them faster through more difficult terrain than any other country in the world. And the gap between China's mountain tunneling capability and the rest of the world's is growing, not shrinking. The numbers make the point plainly. China currently operates more high-speed rail than every other country on Earth combined. A significant portion of that network runs through terrain that required extensive tunneling through the mountains of Guizhou and Yunnan, through the highlands of Sichuan, through the ranges of Shaanxi and Gansu that separate the eastern lowlands from the western interior. Each of those projects taught the engineers something. Each of them added to the knowledge base and to the industrial capacity. The factories that build boring machines, the companies that design ventilation systems, the institutions that train tunneling engineers, that makes the next project less uncertain than the last. This is how industrial capability accumulates. Not from a single breakthrough, but from the compounding of lessons learned across hundreds of projects over decades, producing an ecosystem of expertise and manufacturing capacity that cannot be quickly replicated by a country that has not invested in building it. Norway, Switzerland, and Japan, the three countries with the longest histories of mountain tunnel construction outside China, have world-class tunneling industries built on exactly this kind of accumulated experience. Their capabilities are real, and their track records in difficult geological settings are strong. But the scale of their domestic demand for tunneling is a fraction of China's, which means the pace at which their industries accumulate experience is proportionally slower. When a country in Southeast Asia, Central Asia, or Africa looks at the geography between two cities it wants to connect by rail and concludes that the mountains in between make it impossible, the first call it is likely to make is to a Chinese engineering company. Not necessarily because of politics or because of financing terms, but because the Chinese engineering industry has demonstrated the capability to build through mountains that everyone else concluded could not be crossed. That demonstration happened inside the Hengduan range. And the railway that came out the other side of it is not just a transport connection between Yunnan and Southeast Asia. It is evidence. Evidence that what was considered impossible was not. Evidence that the right combination of machine design, geological intelligence, operational discipline, and willingness to learn from failure in real time can take an engineering problem that 3 international teams walked away from and turn it into a functioning railway line that people ride every day. Every large infrastructure project has a number, a total length, a cost figure, a completion date, a design speed. Numbers are how engineers and governments and investors talk about these things. But the railway through the Hengduan range also has a human story that the numbers do not capture. There is a village called Mengla sitting in a valley in southern Yunnan province. Before the railway, getting to Mengla from Kunming involved a journey that could take the better part of a day depending on road conditions, which in the rainy season between June and September meant depending on whether the mountain roads had been closed by landslides, which happened several times each year. Getting agricultural produce out of Mengla to markets in Kunming cost more in transport than the produce was worth in many cases, which meant that farming in the village was subsistence farming rather than commercial farming. You grew what your family ate. You did not grow to sell. The nearest station to Mengla now puts the village 45 minutes from Kunming by rail. Within a year of the line opening, several farmers in the area near the station had shifted from subsistence growing to commercial cultivation of specialty crops, high-value mushrooms, medicinal herbs, tropical fruits that could reach Kunming fresh the same day they were harvested and sell at prices that made commercial farming viable for the first time in the community's history. A school in the area that had struggled for years to recruit qualified teachers because qualified teachers did not want to relocate to a remote mountain village was suddenly accessible to commuters from Kunming. 3 teachers who had previously declined positions at the school accepted them within the first year of the railway operating. These are small stories. They are happening in hundreds of communities along the line, each in its own specific way, each representing the same fundamental change. The mountain that cut these places off from the larger economy of the region is still there. The geology has not changed. The geology never changes on a human timescale. What changed is what the mountain means for the people who live near it, because there is now a hole through it that carries a train. That is what the engineering is actually for. When Xi Jinping approved this project in 2020, the engineering community knew what the geological surveys said. They knew 3 international teams had walked away. They knew the risks were real and the unknowns were substantial. What nobody knew yet was what would be learned inside the mountain. The hydrogen sulfide at 2 kilometers depth, the hydrothermal system larger than the surveys suggested, the pressurized water pocket that stopped a 4,000-ton machine for 11 days, and the methods that turned those crises into a dataset that will make the next impossible tunnel less impossible than this one was. That is how engineering progresses, not through certainty, but through the willingness to go into the mountain, encounter what is actually there, and figure out what to do about it. I want to know what you think. If you could build a railway anywhere in the world through terrain that currently seems impossible, a mountain range, a desert, an ocean crossing, where would you build it and why? Put it in the comments. I read every single one. Hit the like button if this gave you something to think about. Subscribe to AddEmail if you want to keep finding out about the projects that are changing the world right now without making the headlines they deserve. Turn on notifications because next week we go just as deep on something just as real. The map is being redrawn, one tunnel at a time.